B are empty. This is saying exactly what I just said. Namely, no point of one is a limit point of the other. Okay? Happy with that? This is what it means to be separated. And now we have that notion, we can say what it means to be connected. We'll say a set E is connected if E is not, what? Good. Is not the union of two separated sets. Okay. If you have two separated sets, what do you think we call them? We call this a separation. Okay, not surprisingly. So if you can't find a separation of E, then it's connected. Okay? And so these examples give a clue as to what that means. So let's test our understanding here. What about this example in R2? Let's look at the set E of all rational points that pairs x, y, where x and y are in Q. Is this set connected or not? Set of all rational points, which look like, I don't know, come on. Is it connected or no? No? If you say the answer is no, you have to give me a separation. Find me two sets none of whose closures intersect the other. Can you find one? Oh. How many people think this set is connected? How many people think it's not connected? Then how come you guys aren't giving me a separation? You just have to find two sets. Well, let's see. Would it be okay if I put axes on this? Okay, but there's lots of points on that line, so that wouldn't be a separation. Okay. Okay.
And then another set where x and y are both strictly greater than 5 and strictly less than 6?
No, because we want the separation to be one whose union is the whole thing. And if you do the less than or equal to y and greater than y, it turns out that this is not true because their closures include the diagonal. Okay, nice tries though. Let's. What about this one? Suppose I look at the point pi here. Would you agree that the line at pi has no such points on it? So let's let this side be A and this side be B. Its union is all of E. That is, A is all the points on this side, B is all the points on this side. Union is everything, right? In E. Brian's saying yes, that's good. Can you see why A closure doesn't intersect B? Yeah. Any point on this side of the line can't be a limit point of this side because it has a ball around it that completely avoids this line. If A has any limit points, they'll be on this line, but they won't be over. Okay? So notice the limit points of both sides can actually intersect, but here we only demand that one does not intersect the closure of the other. That's why this definition is important. Now, coming back to this picture, what that means is you actually can allow the open sets to overlap, but they can't do so in points of E. So another way to say that is this characterization is true when you think of E and you use the relative topology on E. That is, you think of E as the whole space. Okay? So I'm going to mention this even though it's not mentioned in your book, and that is another definition is E is connected if in the relative topology, in the relative sense, if E is not the union of two closed or two open sets in E. That is, in its own, if you're thinking of this as its own space. By the way, if it were the union of two open sets in E, then what would the complement have to be? The other set, and it's closed. So another way to say it is E is connected if it's not the union of the same definition with two closed sets in E. This is all in the relative sense. Relatively open, relatively closed. Okay? But if you're viewing it as embedded in a larger space, then you have to use that definition. Okay? Okay. So now the final question is, do we know any sets that are connected? Name one that you think we might want to decide is connected or not. Is the real line